What really lies beyond the limits of our universe? Are we alone in this cosmic immensity, or do other realities exist alongside our own? Our universe, vast and mysterious, never ceases to amaze us. But beyond what our most powerful telescopes can observe, an even more enigmatic world awaits us. A realm where the laws of physics we know may no longer apply, where time and space take on forms we can scarcely imagine. Dear traveler, welcome. Today we're embarking on an extraordinary expedition to the very edge of reality, where science meets imagination, and where each discovery raises more questions than it answers. But before we set off on a new adventure, remember to like the video and subscribe to the channel so you don't miss a thing. Thank you, and have a great trip! We begin our journey into the heart of the solar system. Our solar system was formed around 4.5 billion years ago. It is made up of one star, the Sun, 8 planets orbiting this star, 5 dwarf planets, and billions of bodies, of which only a tiny fraction are known today. At the heart of the solar system, the Sun is the largest object. It is 109 times wider than the Earth. Mercury, the smallest planet in the solar system, and Venus, our neighboring planet, are the 2 closest planets to the Sun. They are so close that their temperatures are far too high for any form of life. Mercury's average surface temperature is 430 degrees Celsius or 806 degrees Fahrenheit, while Venus's average surface temperature is 462 degrees Celsius or 863 degrees Fahrenheit, due to its powerful greenhouse effect. These are both telluric planets like Earth and Mars. Our planet Earth is the largest of the 4 rocky planets in the solar system, and also the densest. As far as we know, it is the only one to support life. As for our neighbor Mars, located on average 220 million kilometers or 136 million miles from the Sun, it stands out for its significant geological past. As we move away from Earth to leave the solar system, look closely as we pass the red planet. It's covered with craters, impact basins, volcanoes, rifts, valleys, dunes, and polar caps. Liquid salt water has even been found. The volcano you see here is called Olympus Mons. It's the highest in the solar system. And here's the biggest canyon in the solar system, Valles Marineris. We now pass through the asteroid belt, a vestige of the solar system's formation, to reach the gas giant planets Jupiter and Saturn. Jupiter is the largest planet in the solar system. It is larger than all the other planets in the solar system combined. The second largest planet is its neighbor Saturn, whose magnificent rings of ice and dust are over 20 meters or 65 feet thick. Saturn has 145 satellites or moons, more than Jupiter, which has just 95. We now pass in front of the coldest planet in the solar system, Uranus. Like Neptune, it is an icy giant. Uranus has 27 moons and 13 dark, almost invisible rings. Its axis of rotation, tilted by more than 95 degrees, gives the impression that it is rolling in its orbit. Above all, this means that it presents the same pole to the Sun for 42 years. Its neighbor Neptune is the planet furthest from the Sun. Voyager 2, the only spacecraft to visit Neptune, took 12 years to get there. Neptune is the windiest planet in the solar system. Its winds can reach up to 2,100 kilometers per hour, or 1,300 miles per hour. Let's not linger too long on this giant ice planet, at the risk of getting caught up in these violent winds. Let's continue our journey towards the farthest reaches of the universe. We still have one planet to see before leaving the solar system, Pluto, or rather a dwarf planet, as Pluto lost its 9th planet status in 2006. Its chaotic orbit, more like that of a comet than a planet, intrigues researchers. Every orbital period, Pluto is closer to the Sun than Neptune for 20 years. We now find ourselves in front of the Kuiper Belt, which marks the first boundary of our solar system. This ring-shaped region is populated by hundreds of thousands of icy bodies over 100 kilometers in length, and several billion comets. It is 20 times wider and 20 to 200 times more massive than the asteroid belt that separates the telluric planets from the gaseous planets. It's time to leave the solar system and continue our exploration of the universe. We've still got a long way to go to reach the farthest reaches of space. We've covered more than 4 billion kilometers or 2.5 billion miles, but that's still a drop in the bucket compared to the immensity of the universe. In our own Milky Way galaxy alone, there are between 200 and 400 billion stars. The Milky Way is one of some 2,000 billion galaxies in the universe, enough to make you dizzy. So let's continue our journey through the universe to discover what lies beyond the observable universe. Our first stop is 4.37 light-years from Earth, to observe the stellar and planetary system closest to our own, Alpha Centauri. The Alpha Centauri system comprises 3 stars, Alpha Centauri A, Alpha Centauri B, and Alpha Centauri C. Alpha Centauri C is the best-known star in this star system. It's also known as Proxima Centauri because it's the star closest to the Sun. Or at least it's currently the closest star to the Sun, and will remain so for another 33,000 years or so. After that, it will lose its status to another star, as the universe is constantly in motion. Proxima Centauri is less luminous than stars A and B, which form a double star. It seems to have been captured by this double system. It is now gravitationally linked to these 2 stars. Probably because it is less luminous than the other 2, Proxima Centauri was discovered later in 1915. At least 3 planets orbit this star. Proxima Centauri B is of particular interest to scientists as it lies in the habitable zone of Proxima Centauri. It looks very much like Earth. It's a rocky planet with a mass similar to our own. It could possibly harbor water, an essential condition for the emergence of life. The only drawback is that it is located 40,000 billion kilometers from us, so it's hard to explore it to find out for sure. However, scientists remain cautious. Proxima Centauri B is nevertheless very close to its star, which is an active red dwarf. It would therefore receive 400 times more X-rays than we do on Earth. If the planet has an atmosphere, it should have been strongly eroded by these X-rays. In other words, it's hard to imagine the evolution of life on this planet. What's more, it's possible that Proxima Centauri B and its star Proxima Centauri are gravitationally locked. If this is the case, it means that planet B always faces its star in the same way. It would therefore be cut into 2 hemispheres, one immersed in permanent night and cold, and the other where it would be far too hot for water to remain in a liquid state. Here again, it's hard to imagine any form of life on this type of planet, unless life has managed to subsist in the transition zone, the terminator. In this transition zone, temperatures could be temperate. Water could remain in a liquid state. And if the atmosphere is thick enough to withstand X-rays, it could even transfer heat from one side of the planet to the other, increasing the size of potentially habitable zones. All these hypotheses have yet to be confirmed. Proxima Centauri b is therefore currently the closest potentially habitable planet to our own. Since its discovery in 2016, the distance separating us from this promising planet has been frustrating and seemingly insurmountable. But it also represents a challenge which has spurred scientists to surpass themselves in developing ever more efficient technologies. An innovative system has recently seen the light of day: processes for Particle Radiation Coherent Synergistic Interstellar Mission Accelerator. It combines a particle beam and a laser beam into a single powerful thrust mechanism. With this technology, a 5-gram probe could reach 10% of the speed of light and arrive at Proxima Centauri b in just 43 years. A 10-kilogram probe would reach Proxima Centauri b in 57 years. Still a long time on the scale of a human lifetime, but feasible. Above all, this technology is promising and speaks volumes about the progress made by science in recent years. Let's continue our journey to the farthest reaches of the universe. We're no longer in the solar system, and we're moving away from the planetary system closest to our own. But we're still in a relatively familiar environment, the Milky Way. The Milky Way is our galaxy. It's not the largest galaxy in the universe, but its dimensions are impressive all the same. It is estimated to be around 100,000 light-years long and 1,000 light-years thick. It is home to between 200 and 400 billion stars, including the Sun, Proxima Centauri, and hundreds of billions of others. It is home to over 100 billion planets. We're still a long, long way from discovering all that's hidden in our galaxy. The Milky Way is a spiral galaxy. Its center is a supermassive black hole, Sagittarius A. Its mass is equivalent to around 4 million times that of the Sun. We are located 27,000 light-years from this center, on the periphery. All the stars in the Milky Way revolve around this center, including the Sun, which takes around 250 light-years to complete a full circle. This means that since its existence, the Sun has made only about 20,000 revolutions around the center of the galaxy. Just as the Sun is just one of the 100 to 400 billion stars in the Milky Way, our galaxy itself is just one of the 2,000 billion in the observable universe. Before the 20th century, we didn't even know there were galaxies outside the Milky Way. Astronomers classified these other, hazy-looking galaxies as nebulae. And yet, some galaxies close to our own are visible to the naked eye. So luminous and voluminous are they. Such is the case of the Andromeda Galaxy, the nearest large galaxy to our own Milky Way. It is bright enough to be visible to the naked eye in the northern hemisphere night sky. It was only in the 1920s that it ceased to be classified as a nebula. The Milky Way and the Andromeda Galaxy are part of a group of galaxies known as the Local Group. They are separated by around 2.5 million light-years, but are approaching each other at a speed of over 400,000 kilometers per hour, or 250,000 miles per hour. At this speed, they are expected to collide in around 4.5 billion years. This collision will not destroy our planet. Instead, it will form a new megagalaxy. Life on Earth is likely to come to an end long before this collision. will probably no longer be around to admire the magnificent starry skies of this new megagalaxy. The local group comprises over 60 galaxies with a diameter of 10 million light-years. Let's explore the local group and discover its most important objects. Let's start by exploring the Andromeda Galaxy. Also known as M31, this galaxy is located 2.55 million light-years from the Sun. It's larger than the Milky Way, with a diameter of 220,000 light-years. As you can see, it's very luminous. It is, to be precise, 25% brighter than our own galaxy. Not surprising, given that it contains around 1,000 billion stars, 2 to 5 times more than the Milky Way. But as the universe is in perpetual motion, the Milky Way may one day be brighter than its neighboring galaxy. Indeed, the rate of star formation in our galaxy is 3 to 5 times higher than in the Andromeda Galaxy. The Milky Way also has twice as many supernovae. Brighter and larger than the Milky Way, the Andromeda Galaxy is also younger. It is thought to have formed only 3 billion years ago when two galaxies collided. At that time, the Earth already existed. As in the Milky Way, it contains a supermassive black hole called M31. The Triangulum Galaxy, or M33, is the third largest spiral galaxy in the local group. It is considered a satellite of the Andromeda Galaxy. You can also observe it with the naked eye from Earth, but only from the southern hemisphere and under the right conditions. The Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy are the 3 largest galaxies in the local group, but they are far from most impressive in the observable universe. As we saw at the start of our exploration of the local group, there are an estimated 2 million galaxies in the observable universe. These galaxies are distributed in a singular way. They tend to aggregate into groups, clusters, or even superclusters, i.e., groups of galaxy clusters. Galaxy superclusters can extend over hundreds of millions of light-years in diameter and contain dozens of galaxy groups and clusters. The local group is itself part of a supercluster of galaxies called the Virgo supercluster, or local supercluster. At the center of the Virgo supercluster lies the Virgo cluster, a galaxy cluster containing between 1,300 and 2,000 galaxies, 90% of which are dwarf galaxies. The local group is located near the edge of the supercluster, in a small filament, and is drawn towards the Virgo cluster. The Virgo supercluster extends over some 200 million light-years. Its mass reaches 10 to the power of 15 solar masses. It has a unique structure consisting of a flattened disk and a halo. The disk contains 60% of the supercluster's luminous galaxies, while the halo contains the remaining 40% of galaxies, including elongated objects. Among the galaxies of note in the local supercluster, along with the Virgo cluster in the local group, you can also see the Hound Cloud and the Virgo II cloud. The Hound Cloud is very rich in galaxies, but contains mostly medium-sized dwarf galaxies. Its most impressive galaxies are the spiral galaxies seen from the edge NGC 4244, 65,000 light-years across, and the galaxy M94, 30,000 light-years across. As for the Virgo II cloud, it groups together several long filaments of galaxies, including the front-view spiral galaxy M61, a magnificent starburst galaxy. The study of superclusters is particularly important for scientists. As we move further away from Earth, the solar system, the Milky Way, and the local group, we gain an even more global view of the structure of the universe and our place within it. We're also more aware of the universe's movements. It's on the scale of superclusters that we can grasp the expansion of the universe, the phenomenon that sees objects in the universe moving away from each other over time. It is on this scale that the red shift of objects moving away from us and the blue shift of objects moving towards us are felt. But to understand the structure of the universe as a whole, we need to go even further afield. For the universe is neither a cluster of galaxies nor a cluster of galaxy clusters. It's far more complex than that, with filaments of galaxies and regions of emptiness. Vacuum regions are located between galactic filaments. They are referred to as relative voids because these regions are not 100% empty. In fact, there may be no such thing as an absolute vacuum in space. Vacuum regions are considered as such simply because they contain very little visible matter. These voids are just as important as galactic regions. They are essential to understanding how our universe is structured. They are the result of the same movements that drive galaxies to group together in clusters, superclusters, and filaments. The local void, for example, is adjacent to the local group. Discovered in 1987 by R. Brent Tully, it is thought to be at least 150 million light-years wide and up to 230 million light-years long. As we've seen, the notion of the void is relative. Like other voids, the local void is described as empty because this area of the sky contains fewer galaxies than predicted by current cosmological models. According to researchers, this void is constantly growing. Concentrations of matter attract each other, and matter escapes from the void, which will expand over time. The local veil, a wide, flat row of galaxies on one side of which the Milky Way lies, is moving away from the center of this void at a speed of 270 kilometers per second, or 170 miles per second. This is just one example of the many voids in our universe: the Hercules void, the Sculptor's void, the Eridan void, the Cattleman's void. All part of a superstructure discovered in 2014 and christened Laniakea. Laniakea is an immense structure 520 million light-years across, yet it still represents only 1% of the observable universe. Laniakea contains 100,000 galaxies like our own, each with around 100 billion stars and 1 million dwarf galaxies. Its mass is equivalent to around 100 billion solar masses. Within this superstructure, galaxies, including our own, move at their own speed of 630 kilometers per second, or 390 miles per second. Taking into account the expansion of the universe, this speed reaches 15,000 kilometers per second, or 9,300 miles per second. By modeling the data collected on Laniakea, scientists have realized that the ensemble forms an immense cosmic spider's web, made up of filaments and holes. This cosmic web is in perpetual motion. Galaxies and clusters of galaxies move through it, as if in a kind of current. The whole is like a neural network. Galaxies and matter draw networks of filaments that go around empty spaces. The most telling image used by scientists to describe this peculiar structure is that of a watershed. Superclusters are the astronomical equivalent of watersheds on Earth, with the difference that it's not water that's flowing, but galaxies. The discovery of Laniakea was incredible. This superstructure, studded with voids and areas dense with galaxies, is not a supercluster. It's something else, a structure like we've never seen before. If we were to predict its future behavior, Laniakea would not maintain itself as a supercluster of galaxies would, but rather disperse, driven by the expansion of the universe. You may think we've identified the largest superstructure in the universe here, but that's far from the case. Admittedly, Laniakea has impressive dimensions, but the observable universe is even bigger. Laniakea itself is attracted by a supercluster even larger than all the superclusters it can contain, the Shapley supercluster. Several decades ago, we noticed that our group of galaxies and the supercluster of which it is a part were hurtling along at a speed of 610 kilometers per second, or 380 miles per second, as if carried by cosmic currents towards a very specific point in space. This location has been dubbed the Great Attractor. In 2006, it was discovered that the Great Attractor itself is attracted by an even larger object, the Shapley supercluster. Not surprising when you consider that this supercluster stretches over 120 million light-years and is the largest concentration of large-scale matter in the nearby universe. This supercluster, located 650 million light-years from Earth behind the Ruler cluster, was first observed in 1930 by American astronomer Harlow Shapley. At the time, the discovery didn't seem all that important. It wasn't until the 1980s, when the mystery of the Great Attractor began to take shape, that astronomers turned their attention to this supercluster. We then realized that the Shapley supercluster is one of the most massive structures ever discovered in the universe. The mass of this supercluster is equivalent to more than 10,000 galaxies like our own. It contains at least 25 galaxy clusters in an area the size of the Virgo supercluster. These 25 clusters are therefore highly condensed. By way of comparison, the Virgo supercluster contains just one large galaxy cluster. For a while, it was thought that the Shapley supercluster was the Great Attractor, the magnet that pulls us and neighboring galaxies together at dizzying speed. And yet, the mass of the Shapley supercluster, although enormous, is not enough to explain such an attraction. The mystery remained. To explain it, another discovery had to be made, that of an immense void located in the opposite direction to the Great Attractor. This void acts as a repulsive dipole, pushing the local group and neighboring galaxy clusters towards the Great Attractor, itself attracted by the Shapley supercluster. As you can see, the movements of the universe are complex. Voids and massive structures act together to create veritable cosmic currents, moving smaller structures at dizzying speeds. To date, we have only observed a fraction of the entire observable universe. However, we assume that the rest of the universe is structured in the same way. This is known as the principle of homogeneity and isotropy. Based on Einstein's work, scientists have established two cosmological principles that govern space-time. The principle of homogeneity and isotropy concerns space. The universe is considered isotropic and homogeneous, meaning that it has no preferred direction. It's the same no matter which way you look at it. It's the same wherever you are. The second cosmological principle concerns time. No matter where we are in the universe, its evolution has been the same. This principle allows us to assert that the distant galaxies we observe at the edge of the universe are statistically similar to the ancestors of our own galaxies. Of course, these principles apply on a large scale, not on the scale of our solar system. But now that we're more than 500 million light-years from our planet, you've understood that we're only talking on a large scale. Is the universe infinite? Does it have an end? Where does the universe end? How far can we observe the universe? What can we learn from observing the farthest reaches of the universe? These are just some of the questions that plague astrophysicists. Some answers are still missing, as you can imagine. We'll certainly never completely unravel the secrets of the universe. But today, we can already define the limits of what is known as the observable universe. The observable universe is the visible part of our universe. Its boundary is called the cosmological horizon. Simply put, it's the boundary between the visible and invisible parts of the universe. It is also the boundary from which electromagnetic radiation can be emitted, or the limit from which a signal can be received. The observable universe is said to be finite because it has a finite age. The age of the universe is the time that has elapsed since the Big Bang, i.e., 13.77 billion years, with a margin of error of plus or minus 0.040 billion years. The observable part of the universe therefore includes all objects whose light has traveled less than 13.7 billion years to reach us. This does not mean that the cosmological horizon is 13.7 billion light-years away. If we take the expansion of the universe into account, it's much further away than that. The most distant signals that can reach an observer on Earth don't actually come from the edge of the observable universe, but from the cosmological background. The cosmic microwave background is radiation that fills the entire universe, but whose region of emission is located at the edge of the observable universe. The emission region of the cosmic microwave background is called the last scattering surface. It is estimated to be 46.5 billion light-years away. The cosmic horizon has thus expanded from 13.7 billion light-years to 46.5 billion light-years with the expansion of the universe. If we describe the observable universe as a sphere, its radius would be 46.5 billion light-years, and its diameter 93 billion light-years. At the center of this sphere is the Earth. If our planet is at the center of the observable universe, it's because observers are on Earth. The center of the observable universe is a relative notion. It simply corresponds to the location of the observer. For an observer on Proxima Centauri b, this planet is at the center of the sphere. On a small scale, the sphere would not be the same as ours, but its radius would be the same. The further back in time we go, the larger the observable universe becomes. In fact, the further away we are from the Big Bang, the more distant objects we can observe as their light finally reaches us. With each passing year, the radius of the observable universe expands by 1 light-year, and new early galaxies are revealed to us. Galaxies at the edge of the observable universe are primitive galaxies because their light has taken billions of light-years to reach us. So when we observe them, it's as they were billions of light-years ago. To observe them as they are today, we'd have to wait several more billion light-years. The observable universe is therefore the part of the universe that we can observe, with a few exceptions. Some regions of the observable universe are not visible, as they are located behind stellar or supermassive black holes. However, theoretical models enable us to guess what lies in these regions hidden from our observational instruments. The complete universe or physical universe is still a different notion from that of the observable universe. In fact, the physical universe contains the observable universe, but also the invisible part of the universe, where galaxies are too far away for their light to have had time to reach us. This universe can be infinite if its curvature is 0 or negative. The question of the finiteness of the universe fascinates researchers and raises numerous paradoxes. Is the universe finite in space and time? Is it infinite and eternal? Let's continue our journey to the frontiers of the observable universe and see what lies behind the cosmic horizon. To understand where the boundaries of the universe lie, it's important to understand how the universe was formed. Observational cosmology aims to use satellite data to confirm and refine theoretical models of the universe's evolution. Today, this is what we observe: a cold universe, transparent to light, and lacunar, i.e., made up of large regions of vacuum with only a few atoms per cubic meter. In the shadow of stars like the Sun, temperatures are extremely low, never exceeding minus 270 degrees Celsius or minus 454 degrees Fahrenheit. The universe is expanding. In all directions, galaxies are constantly moving away from each other. But the universe didn't always look like it does today. If you were to rewind the film of the universe's evolution, you'd see the universe contracting, densifying, and compressing. As matter compresses, its temperature rises, so you'd see the universe's temperatures rising. When you finally trace the origins of the universe back to 13.7 billion years ago, you'd find yourself looking at a completely different universe from what it is today. A universe so dense that its temperature reached that of the Sun's surface. Today, this primitive universe is described as a homogeneous soup of atom-free photons, nuclei, and electrons. An opaque plasma through which photons cannot pass. Matter is uniformly distributed. The universe is much smaller than it is today. It is compact, dense, and hot. It was only after the Big Bang that the universe began to expand and organize itself. Particles in the cosmic soup interact with each other, colliding and creating new particles. Very quickly, the universe begins to expand and cool. Little by little, the particles lose their energy. Everything we've been talking about, the cooling of the universe, has happened very quickly. We're still less than 20 minutes after the Big Bang. Matter and light particles continue to interact with each other. Quarks, some of the smallest elementary particles known, will join together in pairs or threes to form protons and neutrons. Soon, the temperature of the universe is low enough to allow protons and neutrons to combine. The first light nuclei of hydrogen, helium, and lithium are formed. This is the phase of primordial nucleosynthesis. The temperature of the universe continues to fall. Below 1 billion degrees, the creation of light nuclei comes to an end. We are 380,000 years after the Big Bang. Electrons, which have slowed as the universe cools, will recombine with nuclei to create the first atoms. This phase is called recombination. These first atoms are hydrogen and helium. Electrons no longer interact with light particles. The universe becomes transparent to photons. These then propagate in a straight line, forming the cosmic microwave background or fossil radiation. Light particles circulate freely in the cosmic microwave background, enabling us today to trace the history of the universe from that moment onwards. In other words, the cosmic microwave background is like a photograph of the primordial universe, as it was 380,000 years after the Big Bang. We can't look at this photo directly. To find out what the universe was like at that point in its history, scientists have to resort to models. The scenarios developed are based on the laws of physics observed on Earth and observations made in space, in the primordial universe and the recent universe. These models have enabled them to establish the next steps in the history of the formation of the universe. It was only 100 million years after the Big Bang that the conditions were finally ripe for star formation. The birth of the first stars marks the end of the dark ages of the universe. Unprecedented chemical reactions take place at the center of stars. Successive fusions of light nuclei form heavier ones such as oxygen, carbon, iron, or silicon. This is stellar nucleosynthesis. Stars are born at dizzying speed, 10 times faster than in today's universe. When they explode, they disperse new elements into the universe, which in turn form new stars, and so on. Gradually, the universe becomes populated with stars, and gravitational forces group them into galaxies. 800 million years after the Big Bang, the first galaxies are formed. These were dwarf galaxies. They are smaller and closer together than today's galaxies. They often collide, merging to form a new, larger galaxy. This is how our galaxy, the Milky Way, was formed 13 billion years ago. To retrace the Milky Way's history, researchers precisely analyzed the position, distance, color, and luminosity of around 1 million stars recorded by the Gaia satellite. 2 categories of stars were identified: red stars, richer in metals and heavy elements, and blue stars, thought to belong to another galaxy, Gaia Enceladus. 13 billion years ago, these 2 galaxies began forming stars independently. Gaia Enceladus was a dwarf galaxy, and the Milky Way's ancestor was 4 times more massive and richer in metals. 10 billion years ago, these 2 galaxies collided. The stars of Gaia Enceladus and some of the stars of the Milky Way's ancestor were ejected into chaotic orbits, forming the present-day halo of our galaxy. For 4 billion years after the collision, violent episodes of star formation followed one another, until around 6 billion years ago. The remaining gas eventually settled into the disk of the Milky Way, forming what is known today as the thin disk. The formation of the Milky Way is just one example of how today's large galaxies were formed from primitive dwarf galaxies. As we have seen on this journey, all the structures of the observable universe form a gigantic cosmic web, like an immense spider's web. In just a few billion years, we've gone from a dense, hot universe to a cold, patchy, mostly empty one, due to the phenomenon of the universe's expansion. The universe weaves a gigantic spider's web, populated by galaxies concentrated along filaments, at the crossroads of which lie the largest galaxy clusters. All these structures form the cosmic web. The concept of the cosmic web emerged with the beginnings of 3D mapping of the universe. It describes the observed and modeled distribution of matter. Modeled because in some places we can't observe the distribution of matter, either because it's hidden from us or because telescopes can't access it. The filaments of this cosmic web also confirm the Big Bang model. Indeed, the filamentary structure of the hydrogen gas in which galaxies form is one of the predictions of this model, which is widely recognized as the model for the formation of the universe. In 2021, an international team led by Roland Bacon, a CNRS researcher at the Centre de Recherche Astrophysique de Lyon, was able to directly observe the glow emitted by one of these filaments. To do this, the team pointed the ESO Very Large Telescope in Chile, coupled to the MUSE instrument at a unique region of the sky, for over 140 hours. They didn't choose this region at random. They opted for a region of Hubble's ultra-deep field, which until now had been the deepest image of the cosmos ever obtained. The observing campaign lasted 8 months. It then took 1 year to process and analyze the data collected. The team was thus able to obtain images of several filaments as they were, 1 to 2 billion years after the Big Bang, a period crucial to our understanding of galaxy formation. The researchers realized that the glow of the gas came from a previously invisible population of billions of dwarf galaxies, giving birth to numerous stars. These galaxies are too faint to be detected by current means, but are crucial for refining models of galaxy formation. Because the study of galaxies is important for understanding how the universe works and for finally answering the questions we ask about its finiteness and limits. How galaxies form is one of the mysteries of modern cosmology. With the advent of technology, telescopes and observation instruments have become increasingly powerful. It has become possible to observe the universe over longer distances and to study the distant universe. The first study of the distant universe dates back to the 1990s. The Canada-France Redshift Survey, or CFRS, was carried out from 1992 to 1997. It made it possible to study over 1,000 distant galaxies, enlarging the volume of the known universe by a factor of 150. The light from these galaxies took several billion years to reach us. According to the cosmological principles we have seen on this journey, these distant galaxies are similar to nearby galaxies as they were several billion years ago. By studying distant galaxies, we can go back into the universe's past and study galaxy formation. To understand how our galaxies were formed, astrophysicists first analyze images of distant galaxies reconstructed from Hubble Space Telescope observations. But that's not all. They also studied the motions that animate these distant galaxies. To do this, they use state-of-the-art telescopes such as the Very Large Telescope and instruments to dissect the light from these galaxies. Today we know a little more about the internal movements of galaxies, which has enabled us to create models of their evolution over several billion years. In this way, we have deduced that the largest galaxies were formed by collisions between several dwarf galaxies. Astrophysicists continue to search for ever more distant galaxies to confirm and refine current models of galaxy formation. Not an easy task. The light reaching us from these distant galaxies is so faint that we have to pose for several tens, even hundreds of hours to be able to detect them. Even with state-of-the-art giant telescopes, the most distant galaxies appear at best as small specks, and their light spectrum doesn't reveal much information. The search for distant galaxies also tends to answer a question that remains unanswered, a real hole in our history of the formation of the universe. After the Big Bang, the universe was made up of hot, dense gas. The gas cooled, enabling the formation of cosmic objects, stars, star clusters, galaxies. But observations of the universe as it was 10 billion years ago show that the gas in the universe was once again hot and ionized. What happened in the meantime? Was the gas in the universe re-ionized by radiation from the first objects in the universe, in particular by the first galaxies? Technology is enabling us to push back the limits of distant galaxy observation even further. Recently, the discovery of a very old galaxy has once again turned our knowledge on its head. The James Webb Space Telescope has discovered the most distant galaxy, and therefore the oldest. This galaxy existed some 290 million years after the Big Bang, i.e., 13.8 billion years ago. The light from this new galaxy, named JADES GS Z14-0, took 13.5 billion years to reach the James Webb's main mirror. According to NASA, which announced the discovery, this galaxy is exceptionally bright for its distance. It is also very massive, several 100 million times the mass of the Sun. Its characteristics don't match any of the astrophysical models generated by computer simulations. How could such a young, luminous, and massive galaxy have developed in such a short time at the dawn of the cosmos? Is this galaxy an exception? Is it representative of a class of primordial galaxies whose existence was unknown? Is its luminosity the result of long-term evolution or a temporary event, such as a luminous burst or a particularly intense period of star formation? To answer these questions, we'll need to find and observe other similar galaxies. But that's not the only mystery of this very distant galaxy observed by the James Webb. Spectroscopic observations have shown the presence of oxygen in the light of this mysterious galaxy, a complex element that normally only appears after multiple generations of stars, with the fusion of lighter elements such as hydrogen and helium. An astonishing discovery based on our models according to which there was no oxygen or any other heavy element in the matter of the primordial universe. According to the scientists, this is proof that stars much more massive than the Sun existed very early on and evolved in record time, enough to manufacture the first heavy chemical elements in their nuclear cores, then release them into space before this galaxy was formed. The galaxy was then able to capture these heavy elements, which we can observe today. This discovery is one of many made by the James Webb since its launch in December 2021. This space telescope, built by the American, European, and Canadian space agencies, never ceases to amaze us with impressive discoveries about the fledgling universe. Its instruments enable it to see in the infrared, a wavelength of electromagnetic radiation invisible to the naked eye, but which has the advantage of being able to penetrate dusty areas of the sky. Before JADE's GS Z14-0, it was the HD1 galaxy that held the title of most distant galaxy ever observed. Located 13.5 billion light-years away, this galaxy was discovered in 2022. It is thought to have formed just 300 million years after the Big Bang. According to observations, HD1 is actively forming new stars, perhaps more than 100 per year. Again, an astonishing feature for a galaxy of this type. Far-off galaxies continue to amaze us. Only by observing as many ancient galaxies as possible can we better understand how they formed at the dawn of the cosmos. Like the study of distant galaxies, the study of the cosmological microwave background gives us a better understanding of the universe, its formation, evolution, and composition. The cosmological background corresponds to the first photon emission in the universe, 380,000 years after the Big Bang, when light, then trapped in electrons, escaped. It was discovered by radio astronomers Penzias and Wilson in 1964, somewhat by chance, when they were testing an antenna to measure radio radiation from our galaxy. The researchers discovered an emitted signal, identical whatever the direction observed, the cosmic microwave background. What's interesting about this discovery is that it confirms the Big Bang theory. Indeed, it was predicted by astrophysicist Gamow as early as 1948, on the basis of this model of the formation of the universe. To recap, 380,000 years after the Big Bang, the universe was considerably smaller and denser than it is today. Any photons emitted were immediately absorbed by matter, especially free electrons. When electrons began to combine with atomic nuclei and the universe became transparent to light, the first photons emitted radiation that formed the cosmic microwave background. It's called the cosmic microwave background because the emission does not come from a localized source, but is present throughout the observable universe. The emission peak of the cosmic microwave background is located in the microwave range. It is therefore sometimes referred to as the microwave background. You may also have heard the term fossil radiation. In effect, this radiation is a witness to the universe at that distant time, in the same way that fossils are witnesses to species that have long since disappeared. Observations of the cosmic microwave background, a true photograph of the universe at that moment of its formation, have taught us some interesting things. The universe was more than 1 billion times denser than it is today. The temperature was 2,700 degrees Celsius or 4,890 degrees Fahrenheit. What's more, the cosmic microwave background exhibits minute variations in temperature and intensity depending on the direction observed, known as anisotropies. These anisotropies, which have been known since the early 1990s, provide a wealth of information on the structure, age, and evolution of the universe. For British cosmologist Stephen Hawking, the discovery of the cosmic microwave background was the most important discovery of the century. The cosmic microwave background comes from regions that are now more than 45 billion light-years away from the Earth, and which are becoming ever more distant as the universe expands. Today its temperature is only around -270 degrees Celsius or -454 degrees Fahrenheit. Because the cosmic microwave background is located at the edge of the observable universe, it is often regarded as the boundary that separates the observable universe from the non-visible universe. But be careful not to confuse the cosmic microwave background with the cosmic horizon. The true boundary of the observable universe is a layer of plasma composed of quarks and gluons, the elements that bathed the universe for the first microseconds after the Big Bang. This is known as the quark-gluon plasma ring. Thanks to cutting-edge instruments such as particle gas pedals, researchers have been able to simulate the conditions that prevailed at the birth of the universe. They discovered that from the very first moments in the microseconds following the Big Bang, the dense homogeneous soup that made up the universe was composed of particles called quarks and gluons. These particles rattled back and forth as they collided. As long as the temperature exceeded 10,000 billion degrees, quarks and gluons behaved independently and did not interact. As the temperature of the universe dropped, quarks and gluons slowed down. During collisions, they began to agglomerate with each other. After 10 microseconds or so, they linked up in clusters. This association led to the formation of the first protons, neutrons, and hadrons. This cosmic phase transition from the initial mixture of quarks and gluons to protons and neutrons is fundamental to understanding the evolution of the universe. Today's atoms are made up of protons and neutrons, which enclose quarks. These tiny elementary particles remain confined even during violent collisions between atomic nuclei. No one has ever been able to observe a lone quark, but simulations have enabled us to reconstruct this plasma of quarks and gluons. Much to scientists' surprise, this mixture does not behave like a plasma, i.e. a hot gas of charged particles. Instead, it behaves like a liquid with peculiar properties. These simulations, combined with knowledge of quantum physics, have enabled researchers to retrace what happened during the first microseconds of the universe. Quark-gluon plasma was certainly present during the first 20 to 30 microseconds after the Big Bang, an extremely short time in the history of the universe. It's possible that today this strange matter can be found in some very dense stars. However, since we can't observe it directly, This hypothesis is based on models established by scientists using particle gas petals. The quark-gluon plasma ring lies at the final frontier of the observable universe. Beyond it, we are in the unknown. What lies beyond the universe? We have no way of knowing for sure. Beyond the quark-gluon plasma ring, it's pitch black. No light reaches us. Without light, we can't analyze the light spectrum to study the chemical composition of this part of the universe. Faced with this uncertainty, there are several possible hypotheses. Either the universe is finite and has a limit, further away than the one we know, or the universe is infinite, a very delicate notion for science. It's also possible that our universe isn't the only one in existence. The multiverse theory is gaining increasing support, but is extremely complex to understand and explain. To conclude our journey, let's explore each of these hypotheses and try to understand what lies beyond the cosmological horizon. The first hypothesis assumes that the universe has a limit. The hypothesis of a finite universe poses a real paradox, which had already been stated by the Greek Archytas of Taranto in the 4th century BC. If we find ourselves at the limit of the physical universe, somewhere beyond the limit of the observable universe, what's beyond, if not the universe itself? And yet, as dizzying as this hypothesis may seem, it's the one most physicists and cosmologists agree on. Indeed, science doesn't really like the notion of infinity. It's hard to imagine traveling through space for billions and billions of years without ever seeing the end. In this hypothesis, the finite universe could be surrounded by nothingness. Nothingness, not vacuum. There's a difference between the two. Nothingness has no size because it's nothingness. But even this idea of a finite universe surrounded by nothingness brings us back to the paradox. Is this nothingness part of the universe? Could we, theoretically, venture beyond the limits of the physical universe into this region of nothingness? Alternatively, we could consider that the universe is finite but has no limits or edges. The universe would take the form of a hydrosphere, or three-dimensional sphere. A sphere is the two-dimensional surface of a three-dimensional ball, and a hypersphere is a three-dimensional object surrounding a four-dimensional ball. Hard to visualize, but possible. So no matter how far we advance in the universe in a straight line, we always come back to our starting point. Some theories even assert that the observable universe is larger than the physical universe, and that the same galaxy would be visible in several directions, in the form of different images near or far. The hypothesis of a finite universe is gaining increasing support. It is the curvature of the universe that allows us to decide between a finite and an infinite universe. If it is possible, then the universe is spherical and finite. If it is zero, the universe is flat, and if it is negative, the universe is hyperbolic. In the last two cases, the universe would be infinite. The curvature depends on the amount of matter contained in the universe. To calculate the curvature of the universe, we must also take into account the cosmological constant, which accounts for the acceleration of the universe's expansion. This information can be deduced from the study of the cosmological diffuse background, mapped with great precision by the Planck satellite in 2013. An initial value for the curvature of the universe has been calculated from the data collected by Planck. It is very close to zero, to within a few thousandths. With the margin of error, it would appear that the curvature of the universe is slightly positive or negative. The universe would therefore be infinite according to these data. However, the proponents of a finite universe have not said their last word. In 2019, research published in the prestigious journal Nature Astronomy supports the idea of a spherical and therefore finite universe. To reach this conclusion, the researchers behind the study reinterpreted the Planck data. They found that at very small scales, the power spectrum of the cosmic microwave background fluctuations did not correspond exactly to model predictions. They then recalculated all the parameters of the universe and arrived at a curvature of 4% with 99% probability. A positive curvature, therefore, which implies that the universe is curved rather than flat, and is therefore, on a very large scale, spherical. These results do not contradict Einstein's theory of general relativity, who himself defended the thesis of a spherical universe with positive curvature. This hypothesis could even explain certain things that the current cosmological model of a flat universe cannot, such as the acceleration of the universe's expansion. Finally, it could perhaps provide a solution to the flaws in our current model, such as the Hubble constant or cosmic inflation, a theory often criticized as unjustified except by the flatness of the universe. However, not everyone is yet convinced by this hypothesis. Observation of stars and galaxies, on the other hand, describes zero curvature, whatever the calculations. If the scientific community accepts this model of a universe curved at 4%, then we may have to rethink all our calculations and simulations of galaxy formation and structure. Many researchers support the hypothesis of an infinite universe. But this concept, fundamental in mathematics, is less obvious in physics. Take Galileo, for example, who concluded that speed could be infinite. But later, with Einstein's theory of general relativity, it was discovered that speed is not infinite and cannot exceed the speed of light. Galileo simply didn't have the elements to reach this conclusion. Other scientists believe that we create space as our universe expands. The expansion of the universe was observed through telescopes as early as 1929. It then took years for the scientific community to admit that the universe is in permanent evolution. 70 years later, two independent teams discovered that this expansion is accelerating and were awarded the Nobel Prize for this discovery. The universe seems to be stretching like an elastic band. Difficult then to imagine tangible limits. For the moment, it's impossible to decide whether the universe is finite or infinite. With our instruments, we only have access to the observable universe. But if the physical universe were only 15% larger than the observable universe, we wouldn't be able to distinguish between a finite and an infinite universe. And the most recent data we have show a physical universe at least 92% larger than the observable universe. A third hypothesis emerged in the 1980s, that of multiple universes or multiverses. It could be that the universe contains other, possibly infinite universes. This idea grew out of the theory of cosmic inflation. Cosmic inflation would be a phase transition, i.e., the physical transformation from one phase to another. As for example, when water boils, tiny bubbles of steam form and eventually coalesce to form larger bubbles. The same phenomenon may have occurred in our universe. Under the effect of the cosmological constant, tiny bubbles of space-time were born and grew. When they met, they formed a larger bubble, our universe. Outside the observable universe, other bubbles may have formed in the same way, giving rise to other parallel universes. Based on string theory, which reconciles quantum physics and general relativity, researchers have estimated that there are 10 to the power of 500 possible universes. Each universe would have its own properties and physical laws. Some would be empty of matter, as it only takes a very slight variation in our cosmological constant for atoms to fail to form. It's enough to make you dizzy. The theory of multiple universes provides an answer to one of the many paradoxes facing modern cosmology. If there is only one universe, how can we explain the miraculous development of life within it? If there are an infinite number of different universes with infinite variables, then statistically, each universe containing life will be observed internally, while the others will be unobserved. The question of the limits of the universe is not a recent one. We've been discussing it for thousands of years. Back in the days of the ancient Greeks, Aristotle and Plato believed that the universe was very limited, stopping at the fixed sphere on which the stars were drawn. The atomic philosophers, on the other hand, were already pondering the paradox of the finiteness of the universe. Let's imagine that we're approaching the boundary of the universe and we throw a javelin in the direction of this boundary. The javelin will go beyond the boundary, since we all agree that it's not solid. In that case, it will still be in the universe. With Einstein, we discovered that the universe can be both finite and limitless. The most widespread hypothesis among modern physicists is that of a universe contained within itself, filled with a finite quantity of matter, on which its future depends. Recently, some research has been overturning these assumptions, such as that which proved in 2019 that the universe could be spherical rather than flat, with a curvature of 4%. Because we still don't know what lies beyond the universe, the question of its distant future remains very unclear. What will become of our universe? Will expansion continue indefinitely? Will the universe eventually dilute until it disappears altogether? If so, what will replace it? Will the universe go backwards and bounce back in a new Big Bang? Or will it collapse in what researchers call a big crunch? All these questions remain unanswered for the moment, but researchers are not giving up hope. The best way to answer them is to continue questioning and refining our models with ever more powerful instruments, so that one day we may be able to see beyond the limits of the observable universe. How are galaxies born and formed in the universe? And how does galactic cannibalism play out in practice? A galaxy is defined as a collection of stars, dust, and interstellar gas. Gravitation holds them together. Galaxies range in size from 2,000 to several million light-years across, and come in many different shapes. Thanks to the radiation they emit, galaxies can be categorized into normal and active galaxies. The latter have an active nucleus at their center, which is much brighter than normal. In the universe, when galaxies group together, we speak of clusters and superclusters. The galaxy to which we belong is the Milky Way. Today, tens of thousands of galaxies have been counted, and the observable universe is said to contain over 2,000 billion of them. Thanks to their studies and research, scientists have defined three main types of galaxy. The first are spiral galaxies like the Milky Way. These are the most numerous galaxies in the universe. They contain large quantities of gas and dust, as well as a disk containing young stars and a bulge containing old stars. This disk is often extended by one or two spiral arms and is filled with dust and gas stars. The second type of galaxy is elliptical. They are mainly made up of old stars and contain little gas and dust. Their structure is spheroidal. Finally, irregular galaxies, the last type of galaxy, are much less massive and contain young stars. From the very beginning of its formation, the universe must have been very uniform, devoid of stars, galaxies, or any other type of structure. Little by little, it was transformed into a spectacle of shapes and colors, filled with stars, galaxies, and galactic clusters. Originally, the density of the universe was only subject to small deviations from homogeneity due to the incessant movements of particles, stirred up by radiation. Continuously created density perturbations use gravitation to expand. The force of attraction, imposed by their own mass, enabled them to draw in surrounding matter. This is how homogeneity gaps were created in the universe. Hypotheses concerning the formation of galaxies are based on two scenarios. On the one hand, the hierarchical theory implies that the first structures to form were those with a mass equivalent to around 1 million times the mass of the Sun. More massive structures, such as galaxies, were formed by the accumulation of smaller ones. Galaxies gathered in groups and clusters, culminating in imposing structures like superclusters linked by the force of gravity. Another theory, that of fragmentation, argues that the smallest structures originated from the fragmentation of the largest. In this sense, superclusters would have been created first. Then, yielding to the pressure of gas and radiation, they would have collapsed, occupying immense spaces and being subjected to the expansion of the universe. The large primordial structure would have flattened out under the forces of expansion, taking on the appearance of a sheet of dense matter. As it contracted, it would have given rise to filaments stretching over millions of light years, which would then have split into smaller entities that would have become galactic clusters and then simple galaxies. Current research favors the first theory. However, various data still cast doubt on this theory. Indeed, astrophysicists have observed that the most massive galaxies created their stars very early in the history of the universe. This remains a mystery. Several 100 million years after its formation, the structure of the first galaxies begins to take shape. They consist of globular clusters, the central supermassive black hole, and the galactic bulge containing stars. During this period, the galaxy is in the throes of star formation. Then, over the next 2 billion years, matter settles in the galactic disk. However, the galaxy will continue to absorb surrounding matter throughout its lifetime. The evolution of a galaxy can be strongly affected by interaction or collision events. Indeed, collisions are far from rare in the universe. Given the vast distances separating stars from one another, collisions are extremely rare. However, the dust and gas of the two structures mix and interact. The gravitational forces at play disrupt the original structure of each galaxy, forming zones of higher density. This leads to the formation of new stars. In the early history of the universe, galaxies were closer together and more likely to collide. Today, despite the expansion of the universe, galaxies are still showing signs of merging and colliding. Galactic cannibalism sometimes occurs when a massive galaxy collides with a smaller one. As a result, the former literally swallows the latter until it is completely absorbed. Intergalactic interactions occur when one galaxy is disrupted by the gravitational field of another. This can take the form of a minor interaction, as when a satellite galaxy disturbs the arms of a spiral galaxy, or a major interaction such as a collision or merger of two galaxies. Collisions occur when the two galaxies collide at a speed that allows each to continue on its course. Stars do not collide, but gas and dust do. The interstellar medium heats up, and galaxies can see their trajectories deviate. In most cases, their original shape is altered. Another, more violent interaction phenomenon is galaxy mergers. This occurs when two galaxies move towards each other, but neither can free itself from the other's grip. This has major consequences for their metabolisms. In most cases, the two merging galaxies form a single larger galaxy. When one of the two galaxies is much smaller than the other, the merger is akin to galactic cannibalism. The larger one remains unchanged, but dislocates the smaller one and devours it entirely. In the Lynx constellation, two galaxies were caught in the act of cannibalism. NGC 2798 is a barred spiral galaxy 93.9 million light-years away. Its diameter is around 76,300 light-years. NGC 2799 is a Magellanic-type barred spiral galaxy. Its diameter is around 55,400 light-years. NGC 2798 was first discovered in 1788 by William Herschel due to its slightly higher brightness. NGC 2799 was discovered in 1874 by astronomer Ralph Copeland. Just a few years ago, spectacular images taken by the Hubble telescope immortalized a scene of cosmic cannibalism between these two distant galaxies. In the image, NGC 2798 appears like a vacuum cleaner, drawing the stars of NGC 2799 into its center. Although the space between the stars is so large that stellar collisions are unlikely, the sucked-in stars shine brightly and appear to be caught up in an uncontrollable chaos. The Milky Way, our galaxy, is part of a large group of galaxies known as the Local Group. Some 60 galaxies belong to this group. The Local Group itself belongs to a supercluster of galaxies known as the Local Supercluster. Within the Local Supercluster sit dozens of smaller galaxy clusters like the Local Group. The Local Supercluster is centered on a giant cluster of galaxies called the Virgo Cluster. This cluster lies 50 million light-years from the Milky Way. Within the Virgo Cluster lies a giant cannibal galaxy, Messier 87, which attracts and absorbs its neighboring galaxies. The Virgo Cluster is a gigantic cluster located between 48.9 and 71.8 million light-years away. It was discovered by Charles Messier in 1781 when he drew up a map of the most important galaxies, including M87. The Virgo cluster is located in the constellation Virgo. It is thought to contain between 1,300 and 2,000 galaxies, most of them visible through a small telescope. It comprises a heterogeneous mix of spiral and elliptical galaxies. The Virgo cluster is an agglomeration of at least 3 very different subclusters. Virgo A is the one centered on the giant elliptical galaxy Messier 87. It is the dominant group of all the subclusters, composed of a mixture of mostly gas-poor, spiral, elliptical, and lenticular galaxies. Recent X-ray observations by the Chandra Space Telescope suggest that 3 subgroups have merged to form a single cluster. The other surrounding clouds and smaller galaxies are also moving closer to the cluster center. Even more distant galaxies and galaxy groups are finding themselves attracted by the Virgo cluster's gravity and will certainly merge with it in the future. These data imply that the Virgo cluster is relatively young and still forming. But now, back to the giant galaxy we're interested in the direction of Messier 87. Messier 87 is also known as NGC 4486. It is an elliptical supergiant galaxy. Some 50.2 million light-years away, it remains the largest and most luminous galaxy in the Virgo cluster. M87 was discovered by German astronomer Johann Gottfried Kohler in 1779. Charles Messier rediscovered it and included it in his catalog, published in 1781, in which M87 is listed as the 87th object. In the 1880s, Messier 87 was listed as NGC 4486 in a catalog of nebulosities and star clusters compiled by astronomer John Dreyer. In 1918, an American astronomer, Heber Daust Curtis, noted that Messier 87 had no spiral structure, but a curious straight ray, apparently connected to the nucleus by a thin line of matter. It was American astronomer Edwin Hubble who later classified Messier 87 as one of the brightest globular nebulae. In 1926, he created a new classification of nebulae. He included Messier 87 in the class of extragalactic elliptical nebulae with no apparent elongation. In 1956, Messier 87 was recognized as a circular, elliptical, EO-type galaxy. The Virgo A radio source was located in 1947 and confirmed as part of M87 6 years later. The source is the jet emanating from the nebula's core. Since its discovery, Messier 87 has been a favorite target for observation by amateur and professional astronomers alike, thanks to its proximity to Earth and its high luminosity in the sky. But what are its special characteristics? Messier 87 lies on a line joining the stars Epsilon, Virginis, and Beta Leonis near the constellation Bernice's Hare, at the northern limit of the constellation Virgo. The galaxy has an apparent magnitude of 9.59. A simple 6 centimeter or 2.4 inch diameter telescope can spot it, but its jet is difficult to observe without photographic aid, and will require a large diameter telescope and very good observing conditions. According to Hubble's classification, M87 is designated as an EOP galaxy. The EO designation implies an elliptical galaxy showing no flattening, and the P categorizes it as a peculiar galaxy as it does not fulfill all the characteristics of its class due to the presence of the jet emanating from its core. Messier 87 has a core surrounded by a diffuse, extended, dust-free envelope. M87's galactic halo and diameter are much larger than its visible part, reaching nearly 1 million light-years. M87's total mass is estimated at around 200 times that of the Milky Way. Its extended stellar envelope is around 978,000 light-years in diameter, compared with the Milky Way's 326,000 light-years. But how is M87 structured? The M87 galaxy features a supermassive black hole at its center. It has been named M87 asterisk, M87 because of its host galaxy, and the attribute asterisk in reference to the quasi-punctual source of radio waves. It is the first black hole to be imaged by Very Long Baseline Interferometry in April 2019. Its mass is one of the highest for this type of object, estimated at around 6.5 billion solar masses. The radius of its event horizon, the area around it in which no object or even a ray of light can escape the black hole's gravitational field, is 19 billion kilometers, or 11.8 billion miles, equivalent to 2.5 times the distance from the Sun to the Kuiper Belt. Its average density is equivalent to that of air at the level of Mount Everest. Surrounding the black hole is an accretion disk of ionized gas, oriented perpendicular to the jet. The gas is drawn into the black hole at a rate equivalent to about 1 solar mass every 10 years. At its maximum distance, the disk reaches a diameter of 24,800 astronomical units, or around 100 times the diameter of the black hole. The black hole appears to be rotating very rapidly. M87's black hole is offset by around 81.5 light-years from the galaxy's center, and is oriented in the opposite direction to the jet. Messier 87 has a stellar population dominated by old stars, which are population 2 stars containing few elements apart from hydrogen and helium. Little dust remains to form a diffuse nebula. The random orbital paths of Messier 87 stars stabilize the galaxy's elliptical shape. The space between each star is filled with an interstellar medium enriched with chemical elements ejected by the stars during their evolution. Throughout its evolution, Messier 87's interstellar medium has been continuously supplied with elements from Type 1a supernovae. Although Messier 87 is an elliptical galaxy and therefore does not have a dust band like spiral galaxies, optical filaments with a mass estimated at around 10,000 times solar mass have been observed within the galaxy. As a result, M87 is surrounded by a broad corona of hot, low-density gas. The galaxy has a high population of globular clusters. Indeed, one study estimated the number to be around 12,000, while the Milky Way only counts between 150 and 200. These clusters get larger the further away you are from the galaxy's center. Recent studies have revealed that Messier 87 has completely absorbed a galaxy over the last few billion years. Stars from a feast galaxy would have amalgamated with their fellow stars within the cannibal galaxy M87. Scientists were able to confirm this hypothesis thanks to an extended portion of Messier 87's outer halo, which appears much brighter than it would have if the merger had not taken place. The study focused on planetary nebulae, the envelopes of gas surrounding older stars, and not on the totality of stars, which are far too luminous and numerous to be studied individually. The motion of 300 planetary nebulae have been measured at distances close to those of M87. They look like little green lights from Earth, indicating their position and the speed of their movements. To better understand the research, compare it with water contained in a glass and poured into a lake. Even if it becomes imperceptible, it nonetheless generates disturbances that are likely to be visible. This is how the movements of planetary nebulae provide information about past fusion. The study revealed that a medium-sized galaxy is falling towards the center of Messier 87. Gravitational forces are such that stars are now spread over an area 100 times larger than the original galaxy. The stars coming from the feast galaxy are stretched on all sides, causing the peripheral areas of the host galaxy to become brighter. Thanks to the merger, the Messier 87 galaxy has been enriched with younger, bluer stars. Within the constellation Furnace, some 70 million light-years from Earth, lies a vast lenticular galaxy with a disk but no well-defined spiral arms, known as NGC 1316, or Furnace A, or Fornax A. It was discovered by Scottish astronomer James Dunlop in 1826. The galaxy is described as a radio galaxy, since most of its energy comes from a jet emitting radio waves. Its nucleus has an emission spectrum with broad lines of weakly ionized atoms. NGC 1316 has had an eventful history, which was revealed when astronomers took a long look at it and its neighbor NGC 1317 using a 2.2-meter or 7-foot telescope at La Silla in Chile in 2010. While NGC 1317 appears to be a small spiral galaxy with a peaceful existence, NGC 1316 turns out to have swallowed up several other galaxies during its existence. The remains of this cannibalism are still visible. Astronomers have spotted unusual traces of dust within an envelope of stars, as well as smaller-than-average globular clusters. The first clue proves that NGC 1316 swallowed up a dust-laden spiral galaxy around 3 billion years ago. Galactic tidal effects have been spotted at the edge of NGC 1316. These are the remnants of stars torn from their birthplace and hurled into intergalactic space. Their gravitational effects on stellar orbits occur whenever a nearby galaxy approaches. The NGC 1316 galaxy has thus fed off other galaxies, and its environment is still disrupted as a result. It is now the most important source of radio waves in the Furnace constellation, and the fourth most important radio source in the universe. This is because matter is falling into a supermassive black hole at the galaxy's center. This same black hole has been fed by the galaxy's interactions with other galaxies. the black hole's mass is estimated at between 130 and 150 million times the mass of the Sun. NGC 1316 began its meal 3 billion years ago and is still in the process of digestion. Total fusion is currently in progress. Some scientists agree that it will eventually become a system dominated by a large galactic bulge. Although 3C297 can be seen completely alone, some 9.2 billion light-years from our planet, it was once part of a cluster of galaxies. Under the effect of its powerful gravitational force, its neighbors would have been drawn to it and then totally assimilated. According to the study carried out by the scientists, certain traces of a galaxy cluster have been found. Firstly, large quantities of gas were measured, with extreme temperatures of several million degrees. Then, a supermassive black hole swallowing gas and emitting a plasma jet over a distance of 140,000 light-years is also present. With these elements, the team expected to find a galaxy cluster. But in the end, almost all the galaxies are missing. They were certainly attracted and absorbed by the cannibal galaxy. The galaxy 3C297 is now cataloged as a fossil group. This is a galactic system in which some or all of the component galaxies have merged to form a single galaxy. 3C297 is even the most distant fossil group of galaxies ever identified. It will thus continue its solitary life for several billion years. NGC 7252, also known as Atoms for Peace, is a lenticular galaxy found in the constellation Aquarius, some 220 million light-years from Earth. The galaxy was discovered in 1785 by the astronomer William Herschel. NGC 7252 is the result of the merger of two galaxies. Around 1 billion years ago, two spiral galaxies collided, one becoming a host galaxy and the other a feast galaxy. Now, at the center of NGC 7252, lies a spiral-shaped disk, some 10,000 light-years across, undergoing an intense wave of star formation. It would appear that the two bulges of the original galaxies have merged, and that in the distant future, NGC 7252 will become an elliptical galaxy. The tidal tails that form as a result of the collision stretch for almost 500,000 light-years. The collision has given rise to young globular clusters and groups of bluish stars. Also known as Centaurus A, NGC 5128 lies in the constellation Centaurus, some 38.6 million light-years from Earth. This lenticular galaxy was discovered by astronomer James Dunlop in 1826 and is now the fifth brightest galaxy in the sky. It is one of the closest radio galaxies to Earth. Its active galactic nucleus has been the object of study by amateur and professional astronomers for many years. Seen from Earth, Centaurus A is a galaxy with an extraordinary morphology. It resembles a lenticular or elliptical galaxy with a superimposed band of dust. It is this particular morphology that has led to the explanation that it is the result of a merger between two smaller galaxies. NGC 5128 contains an active core due to the presence of a supermassive black hole, from which two opposing jets of matter flow. Old red stars populate the central zone. The central zone is crossed by a curved disk of dust, containing atomic and molecular gases. New stars are born near and inside the disk. The mass of Centaurus A's supermassive black hole is estimated at 55 million solar masses. Research has not yet determined whether this black hole has always been within Centaurus A, or whether it is the result of a merger with a spiral galaxy. The galaxy's core is very compact and shows a variation in the intensity of its radio and X-ray radiation. Linear jets shoot out from either side of the nucleus, expanding into mushroom-shaped jets when they reach a distance of 16,300 light-years. The dust band crossing NGC 5128 is a disk seen from the side, 26,100 light-years in diameter and 652 light-years thick. It is made up of metal-rich stars, nebulae, and dust clouds. Within the dust belt, a burst of star formation began 50 million years ago. The rate of star formation appears to be 10 times higher than in the Milky Way. Centaurus A produces a lot of energy from gas falling back into the central black hole. Some of it is then propelled back into the two jets at impressive speeds. The northern jet is clearly visible, while the opposite southern jet is much less visible and has only been discovered thanks to a few knots. These jets are linear in shape until they reach the interface of the galaxy's interstellar and intergalactic gas, where a shock wave forms and they take on the shape of mushrooms. Their total length is around 30,000 light-years. Thanks to a technique using near-infrared images taken with ESO's 3.58 meter or 12-foot diameter New Technology telescope, astronomers were able to observe Centaurus A swallowing its meal with flawless precision. The little spiral galaxy appeared twisted and distorted. Thousands of star clusters swirled inside Centaurus A, representing the crumbs of cosmic fusion. To witness the meal of a giant cannibal galaxy live in this way remains rare and exceptional. The constellation Pegasus dominates autumn nights. It can be spotted in association with Perseus, Andromeda, and Cassiopeia. These are all neighboring constellations. Pegasus forms a majestic square of stars, the main part of the constellation. Within this constellation, Edward Stephan first spotted a group of galaxies in 1878. At the time, it was cataloged as an aggregate of nebulae, but it was later revealed by Edwin Hubble in 1924 that these were galaxies made up of billions of stars, far removed from the Milky Way. With a magnitude of 14, a telescope of at least 20 centimeters or 8 inches in diameter is required, as well as good observing conditions to catch a glimpse of the quintet. Stephan's quintet is made up of 5 galaxies: NGC 7317, NGC 7318A, NGC 7318b, NGC 7319, and NGC 7320. The first 4 are located relatively close together, around 340 million light-years from the Milky Way. Their spiral arms and disks are highly altered by tidal forces. NGC 7320 is much closer to us, between 35 and 40 million light-years away. These 5 galaxies show clear signs of gravitational interaction. Filaments of gas and stars are escaping from them, as a result of the attractive forces that bind them together. NGC 7318A and NGC 7318B show the strongest interaction. A large proportion of their components have intermingled, forming a zigzag structure from which it's easy to spot their two bright cores. In 2018, the galactic cannibalism of Stephan's quintet was observed in even greater detail. Indeed, thanks to the extreme image quality of the Canada-France-Hawaii telescope, new information has been uncovered about how the quintet formed. While the researchers were originally capturing images of NGC 7331, a nearby spiral galaxy, their attention was focused on a concentration of galaxies in its background. This concentration turned out to be Stephan's quintet. This revealed an extensive red halo of older stars, centered on one of the elliptical galaxies, NGC 7317. These data show that the quintet is still interacting strongly, whereas scientists previously thought the opposite. What's more, NGC 7317, thought to be rather quiet, turns out to be still very active with the other members of the group. Stephan's quintet is indeed the scene of widespread galactic cannibalism. It is a highly coveted object of study for astrophysicists wishing to investigate the collective evolution of galaxies undergoing interaction, collision, or shock processes. In the long term, this cannibalism should lead to the formation of a single giant elliptical galaxy. Within the Eridan constellation, a magnificent pair of galaxies clearly displays its interaction. They lie more than 50 million light-years from Earth. The first stretches over 300,000 light-years in diameter, and the second over 240,000 light-years. These are the NGC 1531-1532 pair. NGC 1531 is a small lenticular galaxy located 54.5 million light-years away. It was discovered by astronomer John Herschel in 1835. It has a high surface brightness and an estimated diameter of around 23,800 light-years. NGC 1532 is a very large barred spiral galaxy. It lies 47.3 million light-years away and was discovered in 1826 by astronomer James Dunlop. Its diameter is currently estimated at around 303,000 light-years. The larger of the two, spiral galaxy NGC 1532, has drawn dwarf galaxy NGC 1531 into its gravitational influence. The latter is now a prisoner, subject to the forces imposed on it by the larger galaxy. In the long term, it will disappear in a total merger with NGC 1532. Thanks to the 8-meter or 26-foot diameter Gemini South Telescope at Cerro Pachon, Chile, an exceptionally splendid image of the NGC 1531-1532 duo has been obtained. NGC 1532 is in the foreground, beset by bands of dust. NGC 1531 lies in the background, but is easy to spot thanks to its bright core just above the center. All along the upper right edge of the front spiral arm, numerous young clusters of bright blue stars appear, born of the gravitational attraction residing between the two galaxies. Messier 51 is the most easily observable pair of interacting galaxies. Simply by using binoculars with 10-time magnification, you can make out the two tiny spots next to each other. The two diffuse stars separate as soon as you use an 80mm telescope. With a 200mm telescope, the two galaxies can no longer hide their bright cores and quasi-stellar appearance. Finally, with a 400mm telescope, the main galaxy clearly displays its spiral arms, which are covered with small knots that are in fact large star clusters. Charles Messier first discovered this galaxy in 1773 in the constellation of the Hounds. It lies more than 30 million light-years from Earth. M51 is also known as the Whirlpool Galaxy. It is the result of the meeting of two galaxies. NGC 5194 is the larger of the two. It is a spiral galaxy. NGC 5195, the smaller of the two, is a lenticular galaxy. The larger galaxy tugs so hard at its smaller companion that the smaller galaxy is completely distorted, making it difficult for astronomers to classify it. A bridge of matter appears to link the two objects, but this is in fact a deceptive perspective effect. Tiny NGC 5195 lies a few 100,000 light-years behind NGC 5194. Around 500 to 600 million years ago, NGC 5195 would have crossed the disk of the larger one. The smaller galaxy would have penetrated the disk from behind towards us, and even made another encounter between 50 and 100 million years ago to reach its current position. The interactions between these two galaxies produced a flurry of new stars. Using the Hubble telescope, astronomers have detected more than 100 ionized nebulae in the larger of the two. In the Sagittarius constellation, one particular galaxy is shaped like a bird. With the scientific names ISO 593, IG008, but better known as Tinkerbell, this galaxy lies around 650 million light-years from Earth. Its wings extend over 100,000 light-years, roughly the size of our own Milky Way. This marvelous star is in fact the result of the encounter between two spiral galaxies and an irregular galaxy, although scientists have long thought that only two galaxies were involved in this collision. Thanks to ESO's Very Large Telescope, a team of astronomers has now been able to study this peculiar triple system in a little more detail. The images reveal two galaxies interpenetrating perpendicularly, forming the body and wings of the creature. The third massive irregular galaxy forms the bird's head. This is where stars are born at a spectacular rate of nearly 200 solar masses per year. It is the system's main source of infrared luminosity, despite being the smallest of the three galaxies. This trio of galaxies strongly resembles a winged creature. The result is a mega-galaxy called the Tinkerbell Triplet. Located in the constellation of the Sculptor, some 423 million light-years from us, lies the Cartwheel Galaxy, a lenticular ring galaxy, also known by its scientific name, ESO 350-40. With a diameter of around 180,000 light-years, it is a larger galaxy than the Milky Way. It was first observed by astrophysicist Fritz Zwicky in 1941. Its name was given for obvious reasons. Its shape resembles that of a wheel, with a hub in the middle, the rim around the rim, and the semblance of spokes running from the center to the periphery. This particular shape is thought to be the result of a collision with a small galaxy around 200 million years ago. Prior to the impact, the wagon wheel galaxy would have had a spiral shape, like that of the Milky Way. The small galaxy would have passed through it, creating a shock wave and a gigantic gravitational disturbance. As the wagon wheel galaxy is of greater mass than the galaxy responsible for the impact, the latter will eventually be swallowed up by the larger one. Thanks to the James Webb Space Telescope, we were able to observe this galaxy in all its splendor, as well as the dust that surrounds it. The collision between the two galaxies has formed two rings extending from the center of the galaxy to its periphery. The first ring contains a lot of dust and gigantic clusters of young stars, making it very luminous at its core. The second ring has been extended for 440 million years. It collides with the surrounding gas, giving rise to hundreds of millions of new stars. A study of the galaxy reveals zones rich in hydrocarbons and other chemical compounds, as well as dust whose composition is very similar to that of terrestrial dust, composed of silicates. It is these zones that take on the spiral ray shape so representative of the wagon wheel galaxy. The Lyra constellation peaks at midnight in early July, passing close to the zenith at our latitudes. It revolves around its brightest star, Vega. NGC 6745 is a very special member of this constellation, 200 million light-years away. It is a pair of interacting galaxies. It consists of NGC 6745A, the main member, and NGC 6745b, its companion. A few hundred million years ago, the small irregular galaxy, NGC 6745b, would have partially passed through NGC 6745a. The latter was almost certainly a spiral galaxy before the collision took place. Its structure is now totally altered. This cannibal galaxy has absorbed most of NGC 6745b's interstellar medium, leaving the latter stripped of most of its interstellar gas and dust. Between the two galaxies lie star clusters around 10 million years old. This is gas extracted from the larger galaxy, which has begun to form new stars in large quantities. The constellation Bernice's Hare lies between Leo and Bouvier, with declinations between plus 13 degrees and plus 33 degrees. It can be seen from almost anywhere on planet Earth. Its brightest star is Beta, with a magnitude of 4.3. The Bernice Hare constellation is rich in galaxies and other telescopic objects. It also features a pair of galaxies in the throes of cannibalism. This is the Mouse Galaxy. NGC 4676A and NGC 4676b form a pair of lenticular galaxies. The pair was discovered by astronomer William Herschel in 1785. They were later listed in the index catalog as IC819 and IC820. The first member of this duo, IC819, is a vast lenticular galaxy. It is an active galaxy some 328 million light-years away. Its companion, IC820, is also a lenticular galaxy, 327 million light-years away. It is also referred to as a low-surface brightness galaxy, meaning that it is a diffuse galaxy whose surface brightness is less than 1 magnitude lower than that of the night sky. They are known as the mouse galaxies because of their long tidal tails of stars and gas. The pair are in the process of merging and will eventually form a single gigantic elliptical galaxy. The luminous star clusters, gas and stars currently present in the tails, will position themselves in the new galaxy or remain in orbit in its halo. In 2002, the Hubble Space Telescope captured an image through blue and orange filters, as well as through a near-infrared filter. This is the most precise image of the mouse galaxy available. Blue cascades in the IC820 galaxy reveal clusters of hot, massive young stars whose birth was triggered by gravitational perturbations when the two galaxies met. Matter flows between the two galaxies can also be observed. In the long tail of IC819 are clusters of young stars separated by brighter regions. This suggests that the star clusters were formed from the gravitational collapse of gas and dust that was originally in place within these zones. The blue then yellow color of the long tails contrasts with the brown of the galaxy core. Due to the gigantic size of the galaxies, the cannibalism process is proceeding very slowly, at an approximate radial velocity of 6,600 kilometers per second, or 4,100 miles per second. Full merger will take several hundred million years. In the Ophiuchus constellation lies NGC 6240, a vast irregular galaxy 352 million light-years from Earth. It was discovered in 1871 by French astronomer Edouard Stephan. NGC 6240 is characterized as a liner galaxy, meaning that its nucleus has an emission spectrum characterized by broad lines of weakly ionized atoms. NGC 6240 is one of the most powerful sources of infrared emission in the sky. They are in fact two galaxies in fusion, emitting gravitational jets of stars, gas, and dust. These ultra-bright infrared galaxies fascinate astronomers because of their powerful luminosity. They are generally the result of the merging of gas-rich galaxies, triggering a period of intense star formation. This, combined with the activity of their nuclei, is what gives them their high luminosity. NGC 6240 has two nuclei, corresponding to the final phase of the merger of the two galaxies. In the long term, only a single galaxy will remain. The supermassive black holes at the center of each galaxy will merge into a much larger black hole in a few tens or hundreds of millions of years. Today, however, they are separated by a distance of 3,000 light-years. Because of this proximity, astronomers believe that the two black holes have been spiraling around each other for 30 million years. Recently, thanks to the use of ESO's Very Large Telescope, details about the black holes have been spotted. In fact, not two but three supermassive black holes, tightly packed into a space no larger than 3,000 light-years, are in place at the heart of the galaxy. Such discoveries tend to confirm a hitherto hypothetical scenario of galaxy evolution. The process of two galaxies merging had already been envisaged, but these results show that several of them can merge at the same time, accelerating the process of forming very massive galaxies. NGC 2623 is a spiral galaxy in the constellation Cancer, some 279 million light-years away. It was discovered in 1885 by astronomer Eduard Stephan. This galaxy has many characteristics. First and foremost, it is a liner galaxy since its nucleus has an emission spectrum defined by broad lines of weakly ionized atoms. It is also luminous in the infrared and qualifies as a star-forming galaxy and an active galaxy. NGC 2623 has a very distinctive shape on the sky. This is due to a major collision and the cannibalism of a large galaxy on a smaller one. A breathtaking image taken by the Hubble Space Telescope has revealed a little more about this galaxy. The scene of cannibalism stretches over 100,000 light-years. Although the merging galaxy is much too far away for us to observe it live from Earth with the naked eye, Hubble has brought back some wonderful details. The two galaxies that now make up NGC 2623 were probably originally spiral galaxies similar to our own Milky Way. In the images brought back by Hubble, they appear to have collided. They were certainly each traveling on trajectories that brought them very close to each other. The gravity of the larger one disrupted that of the smaller one, bringing them closer together until the former literally devoured the latter. Now their orbits are distorted, their initial silhouettes have changed, and two long coils of matter can be seen, stretching over 50,000 light-years each. These are known as tidal tails and are being pulled apart at the start of each galaxy by the gravity of the other. As the collision took place obliquely rather than head-on, the tidal tails appear to be twisting somewhat. During the collision, huge clouds of gas collided, forming stars that can be seen in blue all around the tidal tails. They will only live for a few million years. At the heart of the colliding galaxies is total anarchy. Gas deprived of gravity forms arches and furious star formation takes place. The formation and death of stars leads to the creation of dust, which absorbs light and hides the view of what's going on behind it. In such encounters between two galaxies, the stars are, at this scale, so small that the chances of them colliding with each other are virtually nil. Clouds of gas, on the other hand, are much larger, which explains why they collide, resulting in the formation of new stars. Using techniques to date the stars involved in the collision, astronomers have estimated that the catastrophe occurred less than 100 million years ago, which is quite recent on the cosmic timescale. The chaos will calm down one day, and in a few million years, NGC 2623 will become a larger elliptical galaxy. The evolution of NGC 2623 reminds astronomers of the fate that awaits our galaxy. Within 4 billion years, the Milky Way will collide with one of our nearest neighbors, the Andromeda Galaxy. The two galaxies are heading towards each other at a speed of approximately 430,000 kilometers per hour, or 270,000 miles per hour. The stellar halo of the Andromeda Galaxy is much larger and more complex than that of the Milky Way. Andromeda is a notorious cannibal that has already swallowed up a good number of galaxies in our cosmic neighborhood. But more on that later. Astronomers have attempted to illustrate what will happen in this collision. As in all galaxy collisions, it would appear that the objects contained within, such as stars, will not collide head-on. Proxima Centauri, the closest star to the Sun, is almost 30 million times the diameter of the Sun. On a human scale, it's as if the Sun were roughly the size of a coin, and Proxima Centauri was 750 kilometers, or 460 miles away. On collision, the Andromeda Galaxy will gradually annihilate the Milky Way, and the two will form a giant elliptical galaxy. Names have already been proposed for this new galaxy. One early suggestion is Milkomeda, a contraction of Milky Way and Andromeda. Some scientists, preferring to take into account the greater mass of the Andromeda Galaxy, have proposed the name Andromilka. The fate of the solar system is a matter of conjecture. Scientists have estimated that it would have a 50% chance of being ejected 3 times further from the future heart of the newly merged galaxy than it is from the current heart of the Milky Way. In the event of the solar system being displaced towards the center of the collision, it would be disrupted by nearby supernovae. As a result, the main objects of the solar system would not suffer any significant damage. By then, however, the Earth will already have been a habitable planet for several billion years due to the Sun's increasing power. The Andromeda Galaxy, also known as Messier 31, is our biggest neighbor. With a magnitude of 3.4, it can be clearly seen by the naked eye in a dark sky as a diffuse elongated spot. It is all the more impressive when viewed through binoculars. Its luminous bulb is surrounded by a gigantic disk, the length of which is equivalent to 6 full moons placed end to end. With a 300mm telescope, you can see 2 dust bands and a few stellar concentrations. With a diameter of around 220,000 light-years, the Andromeda Galaxy is the largest in the sky, second only to the Magellanic Clouds. It is thought to contain some 1,000 billion stars, between 2 and 5 times as many as in the Milky Way. It lies around 2.5 million light-years from the Sun, in the Andromeda constellation. The first written mention of the Andromeda Galaxy dates back to 964, in Abd al-Rahman al-Sofi's book of Fixed Stars. It was then spotted by Simon Marius using a telescope in 1612, and photographed for the first time in 1887 by Isaac Roberts. The Andromeda Galaxy is the nearest spiral galaxy to the Milky Way, and is twice as large and more densely populated than the latter. It is sometimes even considered its twin. However, the Andromeda Galaxy appears to have formed 3 billion years ago, whereas the oldest star in our galaxy dates back over 13 billion years. Images of its core, taken with the Hubble Space Telescope, reveal 2 luminous structures. These have long been mistaken for 2 cores, but in reality, there is the true core, and alongside it a simple concentration of stars in close orbit. The Andromeda Galaxy is a coveted subject of study for astrophysicists. They seek to explain the physical characteristics of the galaxy's formation. It appears that the formation of the Andromeda Galaxy was the result of the collision of 2 galaxies. The first was present 7 billion years ago. A second, 4 times smaller, was brought into its path 4 billion years ago. The encounter resulted in cannibalism in favor of the larger one, giving rise to the Andromeda Galaxy between 1.8 and 3 billion years ago. This scenario also provides a better understanding of the composition of the halo of gas and stars that surrounds Andromeda, The latter is about 10 times the size of the galaxy itself, and is made up of diffuse clusters, shells, and giant star streams. The galaxy's cosmic cannibalism is now helping to explain its various components. The giant star streams and shells originate from the smallest galaxy, while the diffuse clusters and disk deformation originate from the largest galaxy. As the smaller galaxy is less massive, it forms fewer heavy elements and stars than the larger one. The Milky Way is the galaxy to which our planet Earth belongs. It is an immense disk of stars. It consists of an intensely bright, compact central region called the bulge, and less dense spiral arms. Our galaxy's disk is estimated to be 100,000 light-years across and 1,000 light-years thick. Since 1991, a team of astronomers has discovered that our galaxy is not a simple spiral, but a barred spiral galaxy, which implies that it has a short bar of stars on either side of the central bulge. It also turns out to have 4 spiral arms. From Earth, our view of the Milky Way is very different, as we observe it from the inside. It appears as a wispy band that encircles the entire sky. The Milky Way is made up of 200 to 400 billion stars, so far away that they are impossible to see with the naked eye. Barely 6,000 are visible without an observatory. Although they appear to be crowded together, on average several light years separate the stars from one another. Today, if there's one fact about the Milky Way that needs no further proof, it's that it's a cannibalistic galaxy. This gourmand has been feeding on its fellow creatures since the dawn of time, and is still in the middle of a meal. A team of scientists recently discovered the remains of a galaxy within the Milky Way. It is believed to be the remnant of a satellite that the Milky Way may have agglomerated early in its history. It has been christened Heracles, a name inspired by the Roman mythological hero Hercules, who plays an important role in one of the stories behind the Milky Way's name. The remains of the Heracles galaxy make up a third of the Milky Way's spherical halo. This encounter, which took place 10 billion years ago, was certainly a momentous event in the history of our galaxy. It's quite astonishing that the remains of Heracles weren't spotted earlier, given the important place they occupy in the Milky Way. But since the Milky Way had to be built from the inside out, it was necessary to study the central zones of the galactic halo, which are very difficult to assess, in order to better understand the mergers it underwent. For 10 years, data were collected through the Apache Point Observatory telescope in New Mexico. More than 500,000 stars in the Milky Way were studied through their chemical composition and velocity measurements. Scientists were thus able to determine which stars came from the Milky Way and which from the Heracles galaxy. Reconstructing the chronology of encounters between the Milky Way and other galaxies is crucial to understanding its current organization, which still bears the traces of this past cannibalism. However, the cannibalism of the Milky Way is not just a story of the past. The Milky Way, which appears as a calm milky band in the sky, is in fact a galaxy as violent as it is destructive. It draws in and swallows up all the smaller galaxies around it. Within the local group, galaxies are inevitably moving closer together. While collisions between stars are rare given the distance between them, clouds of gas are forced together until they compress and heat up. As a result, the largest galaxy devours the smallest. This is how the Milky Way attracts the small and large Magellanic Clouds. These are the two largest satellite galaxies in our neighborhood. The large cloud is around 160,000 light-years from the Sun, while the small cloud is 200,000 light-years away. It is estimated that there are around 3 billion stars in the small cloud, and 10 times that number in the big cloud. The latter is also home to one of the largest nebulae in the universe, the Tarantula Nebula. These two small dwarf galaxies find themselves drawn into the Milky Way by a bridge of matter, forming a ring around its poles. Little by little, the Milky Way snatches matter from these galaxies and brings it to itself. While the Magellanic Clouds were certainly once barred spiral galaxies, they now find themselves completely distorted by the gravitational pull of the Milky Way. And since the mass ratio is favorable to our galaxy, it should eventually annihilate the small and large Magellanic Clouds within its structure. In 1994, random images revealed an overdensity of stars close to the galactic center of the Milky Way. Being too massive to be a globular cluster, it found itself categorized as a Sagittarius dwarf galaxy, named after the constellation in which it lies. It lies 75,000 light-years from the Sun, and it turns out that the Milky Way is pulling this small galaxy towards it, so that its tidal arms are spreading out around the poles of our galaxy. Stars from the Sagittarius galaxy should quickly disperse and enrich the cannibal halo. Another galaxy appears on the Milky Way menu, the Great Dog Galaxy, known as Canis Major. This dwarf galaxy is located in the constellation of the Great Dog. It is currently the closest galaxy to the Milky Way, just 42,000 light-years from the galactic center and around 25,000 light-years from the solar system. It contains around 1 billion stars. The Big Dog Galaxy lies behind the plane of the Milky Way, in a region where stars and gas clouds are the densest, and consequently occulting. This is why it was only discovered in 2003, thanks to a large-scale infrared survey of the entire sky, carried out by a team of astronomers. The Great Dog Dwarf Galaxy is currently being totally dislocated by the tidal forces of the Milky Way. Its center is severely degraded, and a long filament of stars stretches out behind it in rings 3 times the circumference of our galaxy. Scientists estimate that within 2 to 3 billion years it will be completely digested by the Milky Way, and its stars incorporated into the structure of the cannibal. Curiosity about the night sky is one of the oldest in human history. It's easy to imagine early man marveling as much as we do at this bluish canvas cloaked in sparkling stars, and projecting his myths onto it. Today, astronomy and astrophysics are at the heart of our understanding of the physical world. Our knowledge of the universe is growing ever finer, even if in some respects it remains more mysterious than ever. The study of cannibalistic galaxies provides us with a dazzling sketch of large-scale cosmic evolution. These acts of cannibalism are very common among galaxies. Cannibalism is therefore far from being a barbaric act, but rather a natural process for galaxies. This phenomenon has a beneficial effect on stars, promoting their formation in the form of gigantic outbursts. Galactic collisions and mergers are fundamental processes that contribute to the formation and transformation of galaxies over time. Thanks to scientific advances and the development of observation tools that reveal minute details, we can now immerse ourselves in the heart of these cosmic interactions and learn more about how stars, gas, and other elements interact to give rise to new, more complex structures. Research into cannibal galaxies promises many more revelations. These phenomena are just one of the countless pieces of the cosmic puzzle still to be assembled. The mysteries of the universe are immense and enigmatic, and they call on us to continue our explorations and research. Who knows what other treasures await us in the depths of space?